We have some parent function, right? We got x squared, outside of x, root x, x cubed, 2 to the x, log base 2x, right? And we just want to see what happens when you do these changes. We could pull up Desmos, but I think we can gather what's going to happen. If you have y equals x squared and compared to y equals x minus 4 squared, what's the transformation you're going to see? Shift 4 right. We know that by now, right? Because 4 comma 0 is your new vertex, right? So I don't necessarily have to pull up Desmos to do that for you guys. So you shift 4 right. So if you list three key points in y equals x squared, for example, I could do 0, 0. I could do 1, 1, and I could do 2, 4. So I just did the right side of the parabola, right? So how they correspond over here? So what would I do? I would, what guys? Yeah, 4, 5, 6, 0, 1, 4. So essentially what you're doing is you're doing A plus 4, comma B. Because essentially you are letting x minus 4 equal each of those three things. And how do you solve for x? You add 4. So that's what's happening. What is Miss Olson trying to do? How dare she? I'm just gonna have a word with her. John, let's see here. Let's fix this. All right, here we go, guys. We're back. Okay, so next up, so we're gonna get what's happening in parts A, B, and C. Now, what if you have 1/2 x squared? Now, that one's a little funny. So what's going to do, graphically speaking, it's going to horizontally stretch by a factor of 2.
We call it vertical.
You could, but then it would be a vertical shrink by what factor?
One. No,
4. Why 4? Why be a vertical shrink by a factor of 4? What happens if you pull out the 1/2? You get 1/4 x squared. So now it smushes it by a factor of 4. So you can say that if you want. That's totally valid. Let's actually pull up in Desmos so we can see that in a moment. But let me finish writing this. So what's going to happen, because it's happening inside the parentheses, I want to be consistent here. Because it's happening inside the parentheses, we'll say it's impacting x directly. So it actually stretches, does the opposite. Because what's happening, if you look at the parent function, right? The parent function is 0, 0, 1, 1, 2, 4, right? That's the parent function. And so what's going to happen to this one over here, so you're setting each of these equal to 1/2 x. So what would you do to solve for x in each case? Multiply by 2, right? So that's 2, 0, 2, 1. Sorry, that was dumb. What's 0 times 2? I know 0 times 2. I do know this, I swear. 0, 0, 2, 1, 4, 4. Because it makes sense. If I plug in 2, I do get 1. If I plug in 4, I do get 4. I plug in 0, I still get 0. So what's going to do to the graph, it's going to expanded in this direction. Whereas originally it's kind of more like this. See how I took the parent function and stretched it that way by a factor of 2. So what it's doing to each point is you're multiplying every x coordinate by 2. Now, if you want to write y equals 1/4 x squared, that's fine. Then what you're going to do is you're going to divide each of these by 4. So it's going to be a vertical compression by a factor of 4 because everything is 1/4 was before. And when you do state the factor, you always state the factor as a number larger than 1. But if it's getting shorter or fatter or whatever, you're going to say a compression, right? That's what you want to say. If it's stretching it, then you actually say stretch. But you could have done that if you wanted to. So actually, let's explore that because I think that's a good thing to talk about. So y equals x squared. Y equals 1/2. Yeah, so you have a point here, right? At 1, 1. So if you multiply x by 2, you're now over here, right? We're here you have a point at 2, 4. Multiply x by 2, now you're at 4, 4. So that's how it changes. So this point here now becomes that point over here. Now, if you want to think of it like this, so now you think of it as a vertical change. I mean, it's still the same graph, obviously, right? See, here you have a point at 1, 1. So I'm not changing x now. How's y change? We divide y by. So instead of 1, 1, you're not 1, 1/4, you see? It's still the same thing. It's just a different way of looking at it, right? Or here you're at 2, 4. Now you're 2, what? 1. So this point now becomes that point. It still generates the same graph, mind you. It's just a different way of altering the table. That's all it is. So we want to make sure we can differentiate between those two things, even though they're still the same thing. Okay, so keep moving. That one's pretty, very, very straightforward. What happens if you put a +3 at the end? Yeah, shift 3 up. We don't need to draw that. You guys know. Shift 3 up. Again, my 3 key points. This is absolute value now. So 0, 0, 1, 1, 2, 2. Now where are we? 0, 3, 1, 4, 2, 5. So how do things change? A comma
B+3.
B+3, correct. B+3. Good. Okay. Example 3 should be pretty straightforward too. It's anything on the outside of the parent function impacts y only, right? So guess what? I'm gonna multiply y by 3. Yeah, there we go. So in this case, we say a vertical stretch. So it's always intuitive when you're changing y. It's counterintuitive because of the way you undo x. But you vertical stretch by a factor of 3. Because what are we going to do to the y values? We're going to multiply them by. So they stretch, right? That's all. They stretch. So I don't feel like moving the screen, but for root x, 0, 0, 1, 1, 4, 2. So guess what? Now it's going to be at still 0, 0, but 1, 3, 4, 6. It stretches. Yeah, stretches, right? Um, ooh, I like that. Okay, if you do, by what factor? I like that. Tell me. You know, good. You gave me an idea for another test question. Thank you. You're giving me all these ideas. I love it. You should write. We should write a test together. Tina, what's going on? No, to answer her question, if you want to express 3 root x as a horizontal, I love that question. That really is a good question. I'm so excited. It's great. No, put the 3 back inside, right? It has to be root 9x, right? If it's root 9x, what kind of compression is that? How do you, so if you set 9x equal, so it's a horizontal compression by a factor of 9. Because if you compress it, what's going to do this way? Right? It counteracts. It's the same impact. So if you stretch this way, it's the same thing as smushing it that way by a factor of 9. Yeah, of course. So you could express that way. Personally, I think it's easier to do the vertical stretch because it's more intuitive, but it's the same exact thing. Does that make sense? Okay.
By a factor of doing it.
By a factor of 9. So for example, 1/9 comma, because think about it. What if I plug in 1/9, guys? If I plug 1/9 into this, what's root 1/9? 1/3. What's 3 times 1/3? 1. So the y by stays intact, but that changes by a factor of 9, right? I mean, that would be kind of weird, but 4/9, sure, you can do that. Root 4/9 is 2/3. What's 3 times 2/3? 2. So you keep that intact. So it's a point on that graph. These are the same. They are the same. It's just a different way of looking at it. Personally, I think it's easier to look at it from a change of y perspective than Tina's way. But if you like Tina's way, go for it. No. Okay. Yeah.
On a test, what you tell us is keep it like, say it was like this problem, like 3 root x and root x
Mhm.
root 9x. You say keep it the horizontal shift, or keep it
I don't care because it's gonna get the same graph. I don't care because all I'll ask you probably just generate points and draw the graph. It won't matter. Okay. Okay. Next up, yeah, now you know what to expect. That's a times 2 times b. And the previous one, by the way, was a comma 3 times b. That was the previous one, right? Okay, and we have this on the first homework. Something like example 4. So now you're being asked to alter this point. And where will it be after you alter it? So let's figure this out. Okay, 5 is on the outside. Are you changing y, x or y? So -3 comma 6 is on the inside, but it's the opposite. So -9 comma 5. You got to take away 6, right? C, you subtract 1 on the outside. Down. -3 comma 4. Okay, now here you're doing it on the inside, and it's the opposite. It's -1 comma 5. Correct. So here you're dividing x by 3. Here you subtract y by 1. Here you subtract x by 6. Here you multiply y by 5. Okay? Cool? All right. You're still doing great in time. Okay, so now we can have a little fun here. Parent. So we'll do y equals x squared as the parent function. We'll do 0, 0, 1, 1, 2, 4, -1, 1, -2, 4. Usually 3 is sufficient. 5 is kind of safe. Okay, so the cloud method. So you draw like a, you don't draw a cloud if you want, I don't care. Okay, so We're adding 3 to y. I think we're very clear on that, right? We're adding 3 to y. So it's going to be 3, 4, 7, 4, 7. I think we're all clear on that, right? We're adding 3 to y. Questions so far before I move on to x, because that's where I could lose people. Yeah. Now, rest. It's a reverse PEMDAS, right? 2x minus 1. So how am I going to undo that? If I set 2x minus 1 equal to each, how am I going to do it? X plus 1. So, yeah, go, or go ahead. Add 1, divide by 2. We're going to add 1 and divide by 2. So it's x plus 1 over 2. So add 1, divide by 2. 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 Just be careful. I can make mistakes too with the mental math, but I think I did it right. Did I make mistakes? What I make a mistake? Tell me.
I think the first.
Yeah, first one's half. You are correct. I did make a mistake. I did make a mistake.
Yeah.
I did make a mistake. So yeah, so 1 comma 4, half comma 3, 0 comma 4, which kind of makes sense that the vertex is half comma 3. That makes sense. 3 halves comma 7, and negative half comma 7. Remember, transforming y equals x squared, right? So if you were to, trying to think here, if you so desire, it's a little extra work, but if you so desire, you could actually pull 2 out. And then it becomes x minus what? Half squared. So if you want to think of it this way, you could. Because did I shift 1/2 to the right? I did. Did I shift 3 up? I did. Did I stretch it vertically? I did. So you could actually hold on. That is a little bit of an error. I meant to do this. My apologies. Because the 2x minus 1 was squared. My apologies. That was written a little incorrectly. So technically speaking, I didn't vertically stretch by a factor. I vertically stretched by a factor of 4, right? So it got even skinnier, right? But I would much prefer we do it this way, just to be consistent. Because otherwise, if I give you too many options, it gets confusing. But it makes sense in the grand scheme of things if I were to rewrite it in this manner. Yeah. Yep. If I graph this or this, it would be exactly the same with Desmos. Okay, example 6. My parent is y equals root x. So we'll do 0, 0, 1, 1. Oh, what the heck? We'll do 9, 3. Okay, so we're only so what are we doing the y, by the way? Yeah, you gotta multiply by -1 first and then add 4. And you gotta be very careful because if you reverse that, you'll get the wrong location. X, only one thing's happened to x. Yes, x over 2. So 0, half, 2, and 9 halves.
Oh, wait, never mind. Are you writing?
Okay, no worries. No, always question me. I can make mistakes. That's 3. 2, and 1. There you go. Oh, good.
You multiplied by -1 something that I four was on the top.
Oh, so it's always using PEMDAS for y because what we see from when we compare like say root x to negative root x, right? It flips because y gets multiplied by -1, right? But if you do root x plus 4, how are you impacting root x? You're adding 4 to all those values, right?
So X, you do the opposite.
Correct. Correct. Okay. Yeah, I think we're doing fantastic on time. So yeah, let's do y equals 2 to the x. We'll do 0, 1, 1, 2, 2, 4, and what the heck, sort of negative number in. Right? And then this here, the cloud. So what's happening? First of all, nothing's happening at x. Absolutely nothing happens at exponent. 0. So just leave it alone. Don't touch it. What happened to y?
One.
And subtract 3. You got to do them -1/2 first. So you multiply y by -1/2. Subtract 3. Ugh, -3.5. -4. -5. And -3.25, I think. This says asymptotic behavior. What is that asymptotic behavior here? Yeah, gets really close to -3. And by the way, because it flips, is this an increasing or decreasing function? It's decreasing. It's decreasing because it flips. Exponential growth would be increasing. 2 to the x.
Why -1 4?
-1
Why is it 0, 1, 2?
You know?
0, 1.
Because I'm crazy. Because I got a sugar high from all those muffins. Because one of the half cups of sugar is getting in my head now. Thank you. Oh, thanks. Thank one. I don't know why. No, I think the previous problem. Probably that's probably why. We had root x. You are correct. And right, that would have been really weird. You know what? I would have caught myself. I would, because it would be really funky, right? Because as we go to the left, it should be getting towards asymptotic behavior. So 0, -3.5 is right here. -1, -4 is right here. Sorry, 1, -4, my apologies. 2, -5. -1, -3.25. Yeah, because I've been like way over here, been so weird, right? So there is an asymptotic behavior because of the shift of 3 down. Yeah. So actually it would be a decreasing function. No x-intercepts, obviously. Y-intercept, of course, of -3.5. Yeah. Okay. We've got one more to handle. And then we close the loop on this. Okay. So here's what I would do. Make a table so we'll call this a parent. Like, what points do you see on the parent? 0, -2, 2, 0, 0. To heck, I'll use that one also. 2, 2, and 4, 4. my cloud. We're adding 2 to x. 3y minus 1. So you have 3 to x. They 1, 1, 3. Not pitching a perfect game, guys. Sorry, my apologies. Yes, you guys are paying attention. -2, 0, 2, 4, 6. Actually, I think I want real lunch. That's probably why. 3y minus 1. So multiply by 3, subtract 1. Multiply 3, subtract 1. Nope. Multiply 3, subtract 1. Multiply by 3, subtract 1. Multiply by 3, subtract 1. Multiply by 3. So it kind of gets, yes, definitely gets stretched vertically. So like the slope kind of gets steeper, right? In that linear portion of it, as it should. And yeah, it shifts, so yeah.
I think.
That, that make a mistake?
Never mind.
Okay. Okay, cool. Perfect timing. So yeah, so homework will be this. So you're gonna be doing pages 11 through 15. Kind of a hodgepodge of different things here. So that will be the homework. 11, yeah, so it says homework 4 here. I'll put in Schoology. I'll start the quiz. And if you don't mind, you guys putting the dividers up. You guys know the drill.
We start with it. Has to form on the explanation. Wait, Miss, you can start over yet. Oh my God. It doesn't even go in there. Wait, wait, Zach. No, yes, because.
Be mindful of your brackets on season 1. It says 26. No. Don't need to know 5. If I don't say it, then don't worry about it.